There is one organ which causes high blood pressure, and it's not what you think. And there are specific exercises you can use to target and fix your blood pressure easily. No diet, lifestyle changes, or medication required. Check the link in the description below, but for now, today's question.
The question, does a ship float higher in water on a higher pressure day than a low pressure day? Does a ship float higher in water on a higher pressure day than a low pressure day? New answer. I've been thinking about this problem for the past couple of weeks and changed my mind. It depends. In some cases the boat will float higher. In other cases, the boat will float lower. It depends on the density of the material the boat is made of, including the boat's contents, and how much volume is above the waterline versus below the waterline. If the volume of air below the waterline is greater than the volume of solid stuff above the waterline, then the boat will float slightly lower. If the volume of solid stuff above the waterline is greater than the volume of air below the waterline, then it will float slightly higher. This second case is what I implicitly assumed in my original answer since I was talking about the displacement of stuff above the waterline. I implicitly dismissed the air below the waterline because I knew that part cancelled out. Except it doesn't. The weight of air below the waterline does indeed add to the weight of the boat. This was an unexpected result for me. It took a lot of thinking, followed by some analysis to confirm all this to myself, for me to make sure I understood it this time. For a steel boat, which is a lot denser than water, the volume of air below the waterline will typically be quite a bit larger than the volume of steel sticking up above the waterline. So the buoyancy upwards on that steel above the waterline will be less than the weight of the air pushing down below the waterline. As a result, the boat will float slightly lower in the water when the air pressure is larger. If you have something like a solid piece of wood floating in the water, then it will float higher in the water when the air pressure is greater. In that case there is no air below the waterline, and the wood above the waterline displaces air, which will help it rise up. This may turn into a long tutorial. I'll be adding bits as I go, so this may not make sense until it's all done. I'm going to try and explain the thinking that led me to my answer, along with some calculations. First, here's a block of wood floating in water. I copied the wave art here, Water Waves cartoon, clip. Art best. I know that the block needs to displace its own weight in water, and since I've chosen the densities as shown, I know that 80% of the block will be underwater. I am completely ignoring the air for now, but I want to show how the pressures work out to give that result, attributed to Archimedes about 2,300 years ago. Here is our floating block of wood with a representation of the pressure forces acting on it due to the water. There is an equation there for the pressure as the depth, h, increases below the surface. Note, I'm taking gravity to be 10 meters /s math 2/math, for simplicity. It will ultimately cancel out in everything we do, so it really doesn't matter what value I use. Let's give our block of wood some simple dimensions. Let's make it a cube 1 meter on each side. That means it has a volume of 1 meter math 3/math. With a density of 800 kilograms /m math 3/math, it has a mass of 800 kg and a weight of 8,000 N. The pressure forces acting on the sides of the cube are all pushing horizontally and equally, so they cancel out. The only force holding up the weight of the block is the pressure acting along the bottom surface. I claimed that this will float with the bottom at a depth of 0.8 meters. Actually, I claimed that 80% would be submerged, but that's equivalent. Let's substitute a value of h equals 0.8 meters into the equation for pressure. We get that the pressure at that depth is P equals 1000 kilograms /m math 3 / math 10 meters /s math 2 / math 0.8 meters equals 8000 N /m math 2 math. The bottom surface has an area of 1 meter math 2 math, so that pressure acting on that area has a force of 8000 and that is exactly the force needed to hold up the weight of the block. That just confirms that Archimedes' principle works for this simple geometry. Now I want to do something extreme. I'm going to pour a whole bunch of oil on top of the water so it completely covers the block. I've chosen my oil to have a density of 600 kilograms /m math 3/math. You'll have to forgive my ability to paste together the green and the blue liquids. Ignore the white stripe between them. Ultimately, this oil will represent the effect of air, but the density is much greater here to help us see the results. I claim that the block of wood will float higher with respect to the water surface. But I had to wrap my brain around how pushing down on top with some oil would make it float higher instead of lower. Here, I've sketched in the pressure increasing with depth. The pressure increases faster in the water than in the oil because of the greater density. The plan is to calculate where the block floats with respect to the interface between the oil and the water. The depth of oil above the block is irrelevant. It will not affect the answer. But I'm going to give it an arbitrary value and just let things fall out as they will. Suppose the free surface of the oil is 1 meter above the top face of the block. Then the pressure of the oil pushing down on top is math_rho/math. GH equals 600 kilograms /m math 3 times math 10 meters per second math 2 times math 1 meter equals 6000 n /m math 2 math. So the force pushing down on the top of the block is 6000 n. We can easily calculate what the pressure needs to be on the bottom surface to balance that force plus the weight of the block. The force pushing up on the bottom has to be 6000 n plus 8000 n equals 14,000 n. So the pressure there must be 14,000 n /m math 2 math. What we do not yet know is the depth of the oil/water interface. Let's set up an equation for the pressure at the bottom of the block as a function of the distance down from the top of the block to the interface between the oil and the water. Then we can equate that to the pressure we know we must have. Down the right-hand side of the diagram, I've developed equations for the pressures at various depths in order to get the equation I need at the bottom. We equate that to the 14,000 n /m math 2 math. We know the pressure at the bottom must be, and we solve to get h math _1 math. So we see that the block floats with exactly half above and half below the oil/water interface. That is definitely higher with respect to the water than it started. So, indeed, surrounding the upper part of the block with a lower density fluid, oil in this case, buoys it up further and makes it float higher than before. If we replace the oil by air, the effect will be much smaller, but it will slightly raise the block up a little. As the air density increases, the block will rise higher still, although still a very tiny amount, since air's density is so low. Now, what about a boat that has some open space inside? I'm going to make a weird boat. This boat has very thin walls and is made of very dense material, all concentrated down at the bottom. The material has a density of 10,000 kilograms /m math 3 math. That is even denser than steel. But there are metals with greater density. Lead for instance. Or gold. Speaking of Archimedes, I've made the bottom of the boat 0.02 meters thick covering the square meter of the bottom. The walls have zero mass. So this boat has a mass of 200 kilograms. This boat will float with the bottom 0.2 meters below the surface of the water. That's the depth that will displace 200 kilograms of water. Now let's do the same thing with oil all over the top of this, to simulate really dense air. I've drawn it floating lower in the water than where it started. That's because we will find that is what happens. We need to do the math. Here's a diagram for that. I've made the oil exactly 1 meter above the top of the boat again. The equations over on the right are exactly the same as before. What's different this time is the pressure down inside. The bottom of the boat has a thickness of 0.02 meters, so the distance down inside from the oil-free surface is 1.98 meters. Multiply that by 600 ks/m math 3 times math 10 meters per second math 2 math, and we get a pressure of 11,880 n/m math 2 math. Armed with that, we add the 2,000 n weight of the boat to get the pressure in the water pushing up on the bottom of the boat. That pressure must therefore be 13,880 n/m math 2 math. We equate that with the equation at bottom right of the figure. So this is where the boat ends up. The increased density of fluid inside the boat has caused it to sink quite a bit lower in the water compared with where it started. Compared with what we had before, if we reduce the density of the oil, the effect will be less. But even with air, it will push the boat down some. So on the original question, when air pressure increases, the boat can sink lower in the water. Although I have proven it, the condition where the depth does not change is when the volume of air below the waterline is equal to the volume of boat structure above the waterline. Consider this boat. This volume, shaded in red, of the solid part above the waterline, is equal to this volume of air below the waterline. If we did this with oil, the buoyancy of the oil pushing up on the walls above the water would balance the weight of oil below the waterline and they would cancel. For most boats, the volume of metal above the waterline is small compared with the volume of air below the waterline. More like the case I did with the oil above. So, in most cases, increasing the air density will cause the boat to float slightly lower in the water. Phew, that was a lot of work. Sorry for the original response that was incorrect. I'm leaving it unchanged below since people have commented on it. Original answer: I agree with Steve Noskowicz's answer to does a ship float higher in water on a higher pressure day than a low pressure day? Curiously, at the end, he says he would like to hear some critique, but I am not able to leave a comment on his answer. I wonder if he knows he has comments disabled. The effect here is incredibly small. The solid parts of the boat above the waterline are buoyed up ever so slightly by the air. When the air pressure is greater, the air is slightly more dense, so there is a slightly greater upward force acting on the boat due to this. This will cause it to float ever so slightly higher in the water than on a low pressure day. The person who said the higher density air inside the boat would cause it to weigh more is confused. I'm assuming that the air inside is the same density as the air outside. That air is thus displacing its own volume in air, and the buoyancy force on that air is therefore equal to its own weight. The net buoyancy for that air is then zero. I hope that helps. If you need more answers and advice on hypertension, I've included some links in the description.